Post. Screen. Well, welcome. Yeah, I'll take these down. Welcome. Thank you, everyone, for coming to the high performance computing session, high performance computing at high latitudes. And I really appreciate all of you coming to the session today. We have a smaller group, so I think I'll maybe let everyone in the room and online just kind of introduce yourselves first, because I think we only have like 3 or 4 people online.
Yeah, we've got 6.
Yeah, so, oh, that's good.
Including me, so.
And me too.
Yeah,
I'm
so
at-
far.
so far. So I'm gonna turn this microphone around. I think this will work. Let's see what happens. And then maybe everyone can just say hi real quick.
Hi, I'm Allison Bear. I'm a PhD candidate at the University of Maryland.
I am Stefano Potter. I'm a research associate at Woodwell Climate Research Center.
Yeah, Jordan Caroline, work at the NASA Aerospace Flight Center.
I'm Devjani Singh. I'm the Indus lead at Orano.
And then maybe folks online, if you just want to say hi real quick. You can unmute yourself and just say hi. Stefano, why don't you tell them what order to do it in? Like, what do you?
Yeah, let's start with, I see Mary first.
Hi, I'm Mary. I'm a grad student at Montana State University.
Let's go with Andrew.
I'm Andrew. I'm a research assistant at Woodwell Climate Research Center.
Melissa.
Yeah, hi everyone. My name is Melissa Regian. I'm at NASA Goddard and University of Maryland.
And Sandra says, sorry, she's not connected to her mic. She's a grad student at Queen's University.
All right, great. We're just introducing ourselves. If you want to
Hello.
introduce yourself.
I will. My name is Zachary Williams. I'm from NASA Goddard, work
Great.
closely with Jordan.
All right, well, great, thank you. Well, welcome, everyone. This is a little bit of a smaller session, but that's okay. I'm going to start us off. I just have a few slides to show. And let me make this, I can make this go away, which is nice. Okay.
You are upside down
Really?
on this,
How about now?
at least for how I see it, you're upside down.
This is supposed to be that.
No, I can't see it.
I'm just gonna turn off the video in here then. 'Cause I don't know how to make that video come back. Where did the video? I hit the controls and now. Do you see?
No, I
Me
don't
still?
see you.
I think it signed me out of Zoom. I hit the controls and then it was upside down and now I think we're signed out completely. Yeah. Are we even in this? It's like, it just went away.
I just noticed you were having a problem with that.
Yeah.
That is weird.
Oh, but I did hide the controls.
Oh, so you hid the screen sharing.
Yeah, but I thought it was just supposed to come back if you kind of went to this. We did this yesterday in our other session and it was fine.
Usually it like pops up if you
Right.
mouse over.
Yeah.
Interesting.
Hold on, folks online. Still working things out.
Can they still hear you?
Can you still hear us online?
Yeah, we can still
Okay.
hear you. So do you need to switch out of sharing screen at some point, or is this fine? Because I need to go talk to Jerry for a second.
Okay, yeah, this is fine. We'll just keep going like, I think
They
I'm
don't- yeah,
upside down, but I don't think it
well, I
really
can't-
matters.
I just don't see you on the camera at all.
Okay, well, that's good. All
But you can see the slides.
right, that's all we need. Okay, so I am just going to take a few minutes to kind of introduce our session and talk a little bit about kind of what it means to be doing high performance computing as part of the Above campaign. And I have a poster on this if you want more information. And we really put this session together because we wanted to also kind of hear from the user community that's using the above Science Cloud or other high performance computing options to do their research as part of above, or using data from the Oak Ridge DAC, like Debjani is going to talk about, to just kind of hear from you how it's going, how you're using high performance computing in your research, and maybe a little bit about what my son does Boy Scouts now, and they do thorns and roses. And so it's like, what's working well, what isn't working as well, where could we kind of tweak things to make it better or different? And so that's kind of where we're coming from. And I just have a few little slides here just to kind of say that this is really a collaborative effort. And so we have kind of the above campaign in our website. We try to do some data management on our website. We have, for example, this above planning tool in the bottom left corner, where we can show where people are working, when they're working, and provide a little bit of information about the research that they're planning on doing if they're going out into the field. But we also coordinate with the Oak Ridge DAC to help data products when they're ready. We can send metadata to the DAC, and the researchers can upload their data. We also then work with the Above Science Cloud, and there's a connection between the Oak Ridge DAC and the Above Science. The Oak Ridge DAC is, of course, the archive center for most all of the above campaign data. We can work between the Above Science Cloud and the Oak Ridge DAC to send data back and forth. And we're trying to do this connection with the Polar Data Catalog, which is our kind of our collaborators in Canada, to make metadata that is developed through the Above campaign accessible to people through the Polar Data Catalog, which is like the Canadian research as well. So just to kind of give a little overview on high performance computing for above through the Above Science Cloud, it's done on the ADAPT system. So if you hear that acronym today, it's the Advanced Data and Analytics Platform available through the NASA Center for Climate Simulation, so NCCS. And that's kind of a picture of what it looks like on the right there. There are both these Linux and Windows virtual machines, and it's incorporating storage, compute, and cloud computing capabilities. And it's really designed for large-scale data and analytics. And Jim Shute will be giving a talk later on today in the plenary, where he will kind of talk a little bit more about above. And most of you already know about above because you're doing high performance computing, but we also have a huge wealth of digital globe high resolution imagery available. And I think that, Jordan, are you talking about that? Or Zach's talking about that today. So we'll hear more about that. And we do have above data sets spread across 3 different DACs. So it's really kind of a multi-scale project. So we have the L-band data, the airborne data at the Alaska Satellite Facility, which is right down the street from here. And then we have ELVIS data at NSIDC, National Snow and Ice Data Center. And then many of our data sets, 157 as of last week, were at the Oak Ridge DAC. So that is all I was presenting, just to kind of whet your appetites for more discussion. And I'm hopeful that in each of the talks we'll hear a little bit about kind of what your workflow is and how you're using high performance compute to do it. And then if you have some kind of thoughts for how to shake things up a little bit, I'm welcome to hear that as well. Not all of our presenters are working on the Above Science Cloud today. So we have Melissa coming up next, and she's working on a different system, but we're looking, oh, look, it's back now. We're looking forward to seeing her research next. So Melissa, would you like to share your screen?
Sure, yeah,
Okay,
if
so
that is all right with you guys.
Let me
I
stop.
have a question for Liz.
Oh, yeah, okay, sure. Go ahead.
So you mentioned at the beginning, like you saw me and Mary like submit the most jobs, and I primarily use like the above nodes and Prism now too.
Yeah.
Like which compute system or part of it is like most often used in general?
Yeah, so I think right now we see a lot of people using probably the different VM nodes, like the Linux nodes, but I think Prism is starting to get used more and more. And I don't know, Zach or Jordan, you guys might actually have more thoughts on that.
Yeah, we do have more authorization now, many of the Prism nodes.
Yeah, I love it.
Yeah, it has been kind of slowly ramping up because so we have been kind of creating like multi-purpose notebooks that people to actually kind of use.
Oh, cool. Like Jupyter notebooks?
Yeah.
Oh, cool.
So many of our like machine learning that can actually leverage GPU resources.
Yeah,
People can actually just use those notebooks.
Cool. Yeah, I primarily interact with Prism through Jupyter notebooks.
Yeah,
as well. Sometimes I'll submit a Slurm job if I've got everything ready.
But I know I use a lot of the like ILM nodes to just do like data processing,
Uh-huh.
like advanced, enhanced, very high resolution for like processing the high resolution data. I just need to have it running like parallel distributed and have it run for like 12 hours.
Yeah.
And that's the only way to do this.
So I actually don't know what the iLab stuff is. I saw it there as an option.
You're gonna cover that?
Okay.
I'll wait till-
All right, great,
Okay.
okay. All right, Melissa, we will let you go ahead. I think you should be able to just share your screen and go ahead.
All right. Can you see my slide by any chance?
Not yet. Go ahead and can you share it? Or if you can't, I can share yours as well. There should be a green arrow down at the bottom. Well, for me, it's green. There should be an arrow that says share screen at the
I
bottom.
think maybe it doesn't want me to share.
Okay.
Sometimes Zoom on my NASA Mac is very unhappy. So if you could share, that would be great.
I will go ahead and share. Yes.
Thank you.
This is weird because it's not actually showing the.
Yeah.
Oh, there we go. Okay, so there's that.
Okay, yeah, we're good.
And let me get it down to that. I don't want to hide this thing again because then it'll go away. Okay. So I can take mine away and here's Melissa's. Okay, we're just going to leave this thing up here. Okay, Melissa, you can go ahead.
Awesome. Thank you so much. So yeah, as Liz mentioned, my name is Melissa Regin. I am actually more so giving a little advertisement on the Earth Information System, which is a large, I would say, multi-agency now project that started at NASA Goddard last year in a kind of a pilot phase and has since expanded into a follow-on. So before I begin, I'll just give a little shout out to the co-authors listed here, in particularly Sujay Kumar and Chris Hain, who are the heads of the EIS Freshwater Project. So if you go to the next slide. So for anyone who hasn't heard of the Earth Information System or EIS, this is a NASA effort that's really trying to bring together all the different NASA remote sensing data sets, model data sets, tools, and kind of bring them together in a, I would say, easier to access framework, and one that is really focused on open science and open source. I'm sure a lot of you can appreciate that NASA data oftentimes is spread over many places, many different DACs. And so this is one effort to try to make it easier for a science user or a non-science user to access that data and do the analyses that they want with it. So right now there's 4 different topic areas listed here: fire, freshwater, sea level rise, and greenhouse gases. I'm a part of the freshwater team, so that's what I'll be talking about today. And you can see just on our little bullet points here in the bottom half of the slide, what we're doing is trying to bring together remote sensing data, model output, specifically from the land information system, and all these different tools into one system for asking and answering questions about the water cycle. And again, open science is really the name of the game. We've been generating Jupyter notebooks and other tools that just make it easier for people to use the data. And I would say probably the most important component of the EIS project is really working with stakeholders. So in the freshwater team, we have stakeholders across the country and really internationally as well, where we're trying to make sure that we're producing the data that they actually need, that they can then use for decision making. So if you can go to the next slide. So the current iteration of the EIS Freshwater project has 5 different components: one focused on fire and hydrology interactions, one focused on coastal flooding, one on water security, and this includes water quality, one that is taking more of a global view on water availability and how that might change throughout the next 100 years, and then one on science translation with AI. So if you can go to the next slide. So I am helping co-lead the task on global water availability and how that might shift and change over the next however many decades. And what we're doing here is using global simulations and really just trying to understand how terrestrial water storage variability has changed, both in the recent past and through 2100. I guess, and not only are we looking at trends, but changes in seasonality, changes in magnitude, changes in timing. We're looking at TWS and what might be leading to those shifts. So not only natural variability or climate change, but human impacts, of course. So, maybe certain areas in the last 20 years, irrigation has really blown up and become really widespread. That's going to impact TWS. And then, of course, the last bullet point, we're looking at more than just terrestrial water storage. We're looking at soil moisture, snow mass, leaf area index, really all the variables that you might be familiar with from a land surface model. So if you can go to the next slide. We're doing all of this with global model simulations, as I mentioned. So we're using the Land Information System, which if you have not heard of that, that's a tool that was developed at NASA Goddard, gosh, probably 20 years ago now, that makes it really handy for the user to decide what land surface model do they want to use, what met forcing data. It's a really handy framework for kind of developing the model tools that you need. So here we're running NOAA MP at 10-kilometer spatial resolution. And we actually have two separate sets of simulations. So one is looking at the recent satellite record, where we're assimilating the data sets that are listed here on the slide. So these are looking at 2003 to the present. That's what the two figures here demonstrate, just quick figures to make. Looking at the Northern Hemisphere May SWE trend and then July GPP trend. And then we have a whole second set of simulations where we're downscaling CMIP6 GCM projections. So again, we'll be able to use those, the hindcast 03 to the present simulations to capture recent water trends and really importantly, how remote sensing tools are capturing those trends. And then we'll use our projections to look out to the future. So if you go to the next slide. So for anyone who is interested in more information, I really recommend you check out the website eis.mysmce.com. This has a whole lot of information from the original pilot project from last year and will continue to be updated from all of the teams, not just freshwater, as the project continues this go round. So the next slide is my final one. And really, if anyone is interested in more information, if you think maybe these model simulations might be of use to you, we're also developing a lot of finer resolution model simulations, again, trying to look over longer time periods, not just 1 year here or there. Feel free to email me if you have questions or comments. Even the last talk was really useful for me, and maybe we'll be able to hook up with some of the above, the DAX or the above cloud or something, because really, I feel like it sounds like a lot of the tools that you guys have developed go right along with what the EIS initiative of just making the data easier to access, making sure people know where it is, and give them examples of how to use it through Jupyter Notebooks. So I just wanted to give a quick little spiel there. Again, feel free to email me. I'd love to chat more. Thanks.
Great, thanks, Melissa. Did anyone have a question or thought?
Yeah, I have a question.
Yeah, Johnny is gonna.
Hey, Melissa. So is the LIS the only model? So this is kind of a data model integration is what you guys are doing, right? So is the LIS the only model that is on that platform, or are there other models for an ensemble run?
I would say right now it's really being built around the LIS system, but the projections are downscaling like a 25-member ensemble, but again, it's still downscaling within LIS. So right now it's built upon that, but if you have suggestions or comments, yeah, feel free to reach out and we can chat and see what we can do.
Yeah, so we at the ORNL DAC has other, like land system models and other hydrologic models. I don't know, means the funding behind this to incorporate everything is a fuzzy interagency, thing to be worked out. But I would be, interested to, talk with you more on integrating some of our stuffs that are in with what.
Yeah.
That's going to be, in my opinion, if you're running an ensemble of climate models or climate data, then we need to have an ensemble of land system models, right? To capture the uncertainties in the land system models.
Right, yeah.
I think too, this Earth Information System, I wonder if it can work with the Earth Data Cloud, or is it working with the Earth Data Cloud? So
yeah,
yeah,
so I guess another team is developing, MAP is already a tool to help access NASA and ESA data. And then there's going to be another component of that, Veda, which I think will allow people to work on Jupyter Notebooks, or maybe it's the other way around, but this is all part of the same initiative. So I'm pretty certain if data are stored on a NASA DAC and probably other DACs, they'll be able to be pulled in quite simply. At least that's the vision as I understand it.
And what if it's non-NASA data?
I'm not totally sure. That might be a question for Sujay or Chris, whose emails are on this slide here. But I think if the data are available publicly online,
Yeah.
there should be ways using a Jupyter notebook or something to pull it into analyses.
Okay, got it. Thank you.
Yeah, I was just going to provide a comment. So, the EIS software is actually running on a like science managed cloud environment, which is like AWS based cloud environment that is managed by 600. So they do have like NOAA data in there
Oh,
that you can share like on the S3 buckets and stuff. So it's actually available for other things as well.
Okay. Cool. All right. Any other questions online or otherwise? Okay.
Thanks.
Thank you, Melissa. Yeah.
Yeah,
You're next. Okay. All right. Okay, next up we have Zach Williams. So Zach, you can come over here and, or if you want to be over there, I can just tab for you. What do you prefer?
I can click.
Okay, yeah.
Sure. So I'm also going to be talking a little bit about the work that we do in ADAPT with the iLab. So I'm here representing the Innovation Lab at NASA Goddard, which is led by Mark Carroll. And I'm going to talk about different ways we've used machine learning to really perform large-scale data analysis within ADAPT. And we're just going to be going through some examples of how we've used different data sets and how we've analyzed them. So to start off, as Liz already pointed out, ADAPT stands for the Advanced Data Analytics Platform, which gives you access to a very large amount of analysis-ready data throughout different spatial within the above domain, including different spectral bands, different temporal frequencies, and different spatial resolutions that can really be, and the benefit of ADAPT is they can really be used simultaneously to perform. A lot of the conversation this week has been focused on scalability, and ADAPT may be a good platform by which to really take these concepts and try to actually work with them. So as Liz also mentioned, it provides access to high capacity computing resources. And a big problem, as you're all very well aware with big data, is just simply how to really leverage these massive data repositories to provide the best science. And what the Innovation Lab does is it comes in and applies machine learning approaches to really utilize the data to its greatest capacity. So one of the ways we do this, and as we're using a very high spatiotemporal resolution that's been brought into ADAPT via the Commercial Satellite Data Acquisition Program. So we have about 24 million scenes, roughly like 9 petabytes of these very high spatiotemporal resolution data. And right here, one of the examples we're looking from Planet Labs. And what we did here was we created a random forest algorithm applied to these Planet Labs Dove constellation products to really look for surface water extent and look for meter scale surface water, which in the above domain, all these tiny little lakes really add up, so it can provide a better estimate for like methane flux into the atmosphere. And I believe Andrew Mullen is going to talk about some of the very exciting work that he's been doing with these products. In addition, Jennifer Watt has a poster out there that can go provide a little bit more detail. So another way that we leverage these very high resolution commercial satellite data is that we take the Maxar Worldview 2 data and use them to identify permafrost thaw slump. We do this by applying a convoluted neural network, which has really helped with the semantic segmentation of these very difficult to discern features in a region where there isn't a lot of available labeled training data. And additionally, we're able to process Maxar data using either the Polar Geospatial Center or the enhanced very high resolution workflow developed by the iLab to convert the raw NITIFs from these Worldview 2 data into orthorectified geotiffs. And this really helps with the access and availability and really just slotting it into whatever your project is going to be and just helping with the whole accessibility problem. So speaking of label training data, one of the generation of large quantities in which, as you all know, to inform the machine learning algorithm decision-making process generally presents a bottleneck in timeline where you have to have a trained observer go through and create all these label training data. We have a Jupyter notebook that we've been developing that uses k-means clustering to provide unsupervised classification, which This is not a replacement for a trained interpreter going in and creating the labeled training data. This is more of a tool that allows a single analyst to really create more training data in a shorter time frame, which speeds up the bottleneck. And this is available to use on any multi-raster data set that is available within ADAPT. Here's an example with Avarice Next Generation. We've used this on Landsat, and we're currently loading in normalized analysis ready Landsat data from GLAD at University of Maryland that should be up sometime in June. But this is sort of a tool that can be used on all the different products. And one of the applications of these, one of the applications we can apply this wealth of training data to is the MODIS surface water product, which is really just a random force applied to leveraging the daily MODIS spectral reflectance products to create an annual surface water extent map. And this is really an operational algorithm to update to the mod 44W mask. But as an operational algorithm. This is within the above domain specific, but additionally on a global coverage at 250 meter per pixel resolution. Very useful for a reference map. So all of this is to say, just a little plug here at the end, all of these data are available on ADAPT and are available to above researchers. And so you can contact Liz Hoy if you would like to create an account on ADAPT. Should be fairly easy, seeing as you're all above affiliated researchers by virtue of being here. Access to commercial data is controlled by end user license agreement, but again, just something, a box to check, and then you can continue moving forward. And if you would like to apply these machine learning approaches, but maybe aren't very familiar with yourself, the purpose of the Innovation Lab is to help you answer your science goals by assisting in the development of these machine learning algorithms. So, and you can contact Mark Carroll for more information regarding that. So thank you. I'd like to answer any questions.
Yeah. I'm just curious about the Boslot mapping. Like, what was the location you were doing that? I have a colleague, Yuli Wang. He's probably giving one of the talks at permafrost is today.
So
he's in Siberia. So I'm just curious where you're.
This was within the above domain. So we're concentrated. So the ADAPT contains data sources for the entire globe, multiple, as Liz mentioned, just constantly growing and evolving. But we wanted to focus this talk specifically within the above domain, which ADAPT was originally designed to support. Turns out it was a great idea and everyone wanted in on it. So we're focusing on the above domain right here. So Alaska, I'm not sure where this where exactly was, but it's in the above, yeah, in Alaska somewhere.
Yeah, that's what I okay.
Yeah, we put some different locations in Alaska.
Oh, cool.
So just trying to see how we could identify something more than regional locations.
Yeah, cool.
So does Mark really, he kind of works with investigators if they want to try to start using some of the ADAPT tools?
Yes, so that's the positive. The Innovation Lab is really sort of the segue into ADAPT. If you have a great science idea and know that machine learning is going to assist, which for the way that modern data science is, it will assist, it will be beneficial. Mark, you can contact Mark and we'll set up a plan and meetings to see if we can move forward and work together on that.
And that's something that kind of, above helps to kind of fund the Above Science Cloud. And I think through some of that kind of funding, there's the ability to kind of work with the Innovation Lab some. So if there are kind of science questions you want to answer and getting stuck, it's possible we can connect you to the Innovation Lab and Mark to kind of get some of that started.
Facilitators, that's what we'd like to help with.
All right, thanks, Zach.
All right, well, thank you very much.
Yeah.
Next, we have our co-moderator, Stefano Potter, who is really a power user of the Science Cloud, I gotta say. And so I was very thankful that he could give us a talk today.
Yeah, thanks everyone. So I'm going to be talking today about how I've got a project that I started a couple of months ago that's going to be mapping. The aim of the project is to map circumpolar wildfires at Landsat or 30-meter resolution. And I'm using a convolutional neural network approach, which Zach just talked about. So for each component of that project, I'm going to go through a little bit of which part of the high performance computing I use. So before I get into the actual project and how I do everything, I kind of just want to go through my standard data processing pipeline, regardless of the project itself. I generally go through these 5 steps. So the first step being, data acquisition or data gathering. The second one is exploratory analysis, so data exploration, data preparation, pre-processing. After that, I can go into the modeling phase, then deploy the model, evaluate it, see how well is it performing, and then finally that leads to understanding. In this case, where are wildfires occurring, how are they changing through space and time, etc. So starting with that first step, which is data gathering, this is the only step in the pipeline for this project that I don't actually use the ADAPT system. And for this, I do use Google Earth Engine, and that's primarily because I'm using Landsat 8 right now, satellite data as my input to the model. And Earth Engine just makes it really, really easy to process this data. I know Landsat is on ADAPT. Because what I'm doing is looking for each individual fire polygon in Canada, I'm looking through all these bands. So the visible bands, near infrared, shortwave infrared, some calculated indices such as the normalized burn ratio, NDVI, NDII, which is like moisture content of vegetation. I do pre and post fire image differencing to really make the fires pop out in the imagery. Landsat is super, super useful for that. So as an example, here's a fire in 2014 in the Northwest Territories. And what you're seeing right now on the right is a fire polygon is collected by the National Burned Area Composite in Canada. So that's like my ground truth data for the model. And underneath it, what you can see in red here is the fire coming through in what is called DMBR. So that's just the difference in the pre and the post fire NBR, or the normalized burn ratio. So for each of these fires, I calculate these indices, again, pre and post fire, and then I export those directly to ADAPT. And then I do the rest of my computing in there. So that leads me into kind of the second step of my data processing pipeline, which is data exploration right now. So what you're looking at is in the blue, or what is 0, is where pixels are not burned, and based on the ground truth data, and in orange is the burned pixels. And I'm just comparing the distribution of, what are these different bands? How are they reacting in fire versus non-fire areas? This kind of gives me an idea of like, what are the most important variables going into the model? It gives me, some intuition in what the model might be doing behind the scenes, especially for neural networks, which are really hard to diagnose. So here you can see clearly like DMBR, it's a well-studied thing, phenomenon in the fire literature. It's separating the fire really, really well. It's probably the most important variable. But information is still being pulled out by differencing NDVI, even the visible bands, but I'm not going to show you all the violin plots. But they're all important, but I can see what is probably driving the model. Continuing in the second step of my pipeline, which is more of the data preparation. So one of the key requirements of convolutional neural networks is they require single-sized input images. Fires, on the other hand, so if you look at this fire, this is in Alaska on the left-hand side. This is a fire, I forget what year it is, but the dimensions of this burn area is like 10 by 15 kilometers. A fire right next door in a different year might be 5 by 5, some might be 20 by 20. That's a little bit of a problem because I need to only use a single size input image. So what I need to do is break those fires into smaller tiles of 256 by 256 pixels. So what you can see on the right here is in the blue is those tiled polygons. And I forgot to mention, for the violin plots, all that data exploration, I do that in the Windows VMs. And I should mention, I only do it in the Windows VMs because I'm looking to use RStudio. If there was RStudio server, I would probably save Ben a lot of headaches on the support side, I think. But I don't know how much demand there is for that. If I'm the only one using it, probably not worth it. If other people like it, might be a good idea to implement. For this tiling effect, though, that I'm talking about here, where I'm breaking all of these individual fire polygons into the smaller tiles, I'll get my script working in a Jupyter notebook or something like that. And then once I have that script ready to go, I can just submit batch jobs through Slurm, which is great. And then it can really go through those nodes and just pump them out really quick. So then after I get all of my images, my fires tiled into these smaller subtiles, I can get to my final modeling, or the third step, which is the modeling process. I'm not going to go into a super in depth about what the convolutional neural network is. This is a standard UNet++ structure. It's widely used now for image segmentation. I feel like 5 years ago, everyone was using random forests. UNet++ and these different segmentation models are becoming more and more used. And I think over the years, you're going to see them quite a bit in people's research projects, especially as it relates to remote sensing. So a key feature too of these convolutional neural networks is they use a process called gradient descent, which is essentially iterating through the data and minimizing a loss function. That really requires a lot of matrix computation, tensor computation, and GPUs are super, super useful for this because it can really speed up those iterations. So I do all of the modeling on the Prism side of ADAPT because they have that GPU support, and it can really help me speed up this part of the processing. So what you're looking at here is on the left-hand side is what's called the model IOU, or intersection over union. You can roughly think about this as an accuracy metric. A score of 1 would mean your model is working perfectly. So what you can see here is, the epochs are the iterations. So here I think I'm iterating maybe 80 times. At the very start of the modeling process, it's using random weights. The model's not learning anything yet. As I go through more and more time, the model starts to learn the data through these iterations in this gradient descent process. My model right now, which I'm only training in Canada and only Landsat 8, eventually we're going to use all the Landsats, Sentinel-2s. I'm getting a performance of about 0.85 for the model IOU. You can even see it start to overfitting there. I don't need to train it this long. I'll probably introduce like data augmentation to help with this too. And you can also just see on the right-hand side, the loss function decreasing over time, which is what you want to see. And another, really useful part about the Prism Jupyter notebooks or the GPU support is I can try all sorts of variations of this model. I can use different input bands. I can use different subsets of the data, augmentation. DeepLab version 3 is another type of segmentation model. So I can compare these things, which is you really need to do. You shouldn't just take the first model you see. And you can see here, my best model is getting an IOU score, about 0.84. And then finally, I deploy this model. And what I did is I took this model that was only trained in Canada and I predicted it in all of the Alaska fires using the Alaska Large Fire database. And it generalizes pretty well. The IOU score there is about a 0.82. The fire behavior in Canada and Alaska is similar, but that's what I want to see. I want to make sure the model is still performing well in areas it's never seen. So what you see here is a variety of fires in Alaska. If you look in the panel Bs, that black outline is the ground truth data. That's the Alaska Large Fire Database data. And then within that is the predicted fire probability, where the higher red colors is a higher likelihood of probability of burning. On the bottom is just some of the input variables, such as DMBR and NDVI. So what I think is really cool is if you look particularly on the fire on the right-hand side in panel B, you'll see some yellow areas, which we're not predicting any burning there. DMBR is also saying it probably didn't burn. Part of the Alaska Large Fire database, they're not trying to map unburned patches. They're just going around the fire in a helicopter, et cetera. So even though, my model is going to say that's an incorrect prediction, in reality, that's probably a true, like a representation of burned area, which I think is really cool. And then here's just some more examples. The model seems to be working pretty well. It's staying within the bounds of the ground truth data. We're essentially going to expand this out to more sensors. We're going to go to hopefully Eurasia as well, Siberia specifically, and then hopefully keep improving things and understand fire burned area a little bit better. Thank you, and I will open it to questions. The next step. So the next step is because I'm only we tried to keep things as simple as possible at the start. That's why we only use Landsat 8. Combine it with Landsat 5, the Sentinels, there's going to be some harmonization we need to do there. Make sure that's still working in North America, and then bring it to Eurasia. We know Eurasia is going to be more difficult. So there's stand replacing fires in North America, Canada, and Alaska at least. They're not always stand replacing in Eurasia. There's also more grassland fires, which recover even in the same season. So we're going to have to, it's going to be, the methodology is going to have to be altered there a little bit more.
I have a question. So for some of the newer fires in Alaska, I think the Alaska Large Fire Database is like pulling data from MTBS.
We're gonna do the exact same thing and predict it on MTBS.
Okay. Well, I was just wondering because then it's like your MTBS is based on Landsat data, and then you have an algorithm based on.
There's some circularity there. Yeah. Yeah, it's true. But when we go to the actual like final prediction stage, we're not going to be using any of that ground truth data. So as long as it's still generalizing, even though it's based on Landsat there, we feel pretty comfortable with it still.
I know you said you're using Google Earth Engine right now because that's where like the Landsat 8 data is. But what about when you put like Landsat on Adapt? Would you be able to use that?
So and it's a good question. I've thought about it, but my understanding is I would have to go find each individual Landsat tile, right? And then I would have to mosaic it for the fire and then difference the pre and post.
Well, Jordan and I are currently retiling the normalized Landsat data to the above reference grid so it should be a little bit easier to find the corresponding.
So, but say, okay, so let's say I say the year is 2005, I have a fire.
Okay.
So I just want to go to 2006 and 2004 for a certain area, take every scene within that year, take the mean of it, and then difference it. Would that be pretty easy to do?
It should be. We can talk because
we should discuss
we should
this.
discuss that because we're in the process of building it. So you're in
we should
the end user.
Because if I can use it that way, I could take that whole part out.
Because it's going to be based on the above reference grid. So
Right.
So each tile.
And it will be in Siberia.
That's not in Siberia though.
Eventually, we're going to go to Siberia. Yeah.
Eventually, well,
But that would be the only limitation and stuff.
I believe we have options to download the.
Yeah, we should discuss it. And basically your latency is about the same as Earth Engine, such as like getting Landsat 9 in, etc. Yeah, we should discuss. I'm intrigued by this. Yeah, I like that a lot. Yeah.
Well, those are the questions that. And what about RStudio on server on Linux?
I was going to provide a comment on that. So
Oh, sure.
We do have a Anaconda environment on Jupyter that has the R.
Yeah. Oh, so you would run it through the Jupyter notebook
So
instead of our studio
can-
server.
There is already an environment there. You can install additional packages on it.
Well, so yeah, what I do with the Jupyter notebooks is I'll do like my own custom Conda installs. I know you can do it with or I have them that I run through Slurm, and then basically you can change the kernel.
Yeah, just change the kernel to an R
Okay.
kernel that is in there, and you can, like I have done visualizations on R, like it was.
Sure.
Studio.
I'm gonna check this out because yeah, usually when I go to the Windows VM, I'm just trying to get on R, and like the temporary files always seem to clog up the C drive. And Ben emails me, and he's like, "Hey, there's no space." And I'm like, "Sorry."
I would suggest we'll try that out.
Yeah, I will. Yeah.
Just
Yeah.
only kernel. If you want more packages than the kernel has, you can just like only. kernel.
Oh yeah, I've gotten around that. Yeah, I've gotten around that problem before. Yeah. Yeah, it's a good idea. All right, thanks everyone.
Well, thank you. See, we're stimulating discussion. I'm glad Jordan and Zach, you guys are here. Great. Okay, I think next, Andrew and Mary, we have you guys up. So shall I just go ahead and share maybe, and then you can tell me when to go next?
Yeah, that works.
Okay.
Awesome.
All right, go ahead.
So hi, everybody. My name is Andrew Mullen. I'm a research assistant at Woodwell Climate Research Center. And I'm here virtually with Mary Farina, who is a PhD student at Montana State University. And today we are going to give you all a few examples of how we're using the Above Science Cloud to address certain above research goals. And so we're going to give a few examples of different resources available on this shared compute platform and how we're kind of implementing them in our workflows. So you can go ahead and go to the next slide. So this first project, Zach Williams briefly touched on it. This sort of builds off of work from him and a handful of others, and has also benefited considerably from working with the folks at the iLab and Mark's group. And so essentially what we're doing here is we are using a convolutional neural network, similar to what Stefano just talked about, to map lakes and ponds in Alaska at a 3-meter resolution using PlanetScope imagery. And essentially all of the major processes are taking place on ADAPT. And I'll talk a little bit about specifically what we're doing or what we're using ADAPT for. So could you go to the next slide, please? So with regards to data, we are using ADAPT for acquisition and storage of essentially all of the data being used. So we're using a lot of Maxar worldview imagery from the NGA archive that's hosted on ADAPT. And then Mark's group actually provides that as a orthorectified surface reflectance product that helped us out a lot when we were developing our training data set. We also utilized a couple different digital elevation models that are hosted in public repositories on ADAPT throughout various stages of the project, and the ease of access to these products made it really easy to implement them and use them in our processing and analysis. And then the bulk of the data is coming from Planet Labs. We're downloading multiple terabytes of planet imagery and storing it on ADAPT for both training the model and then running model predictions for these water bodies. So as far as development goes, basically the only piece of the puzzle that we didn't do on ADAPT was the training data development in ArcGIS. We elected to use ArcGIS on our local desktops just for stability and latency reasons. But all of the code development took place in Jupyter Hub on ADAPT. I really enjoy using Jupyter Hub. It's a nice, really modular kind of development environment that certainly has grown on me since I've started using it. And then we're training our model by distributing it on multiple Prism GPUs, which considerably speeds up training of our model. And this allows us to have more time to kind of experiment with different data inputs, different model hyperparameters. And so it's really nice to be able to do this to speed that process up. And then we're currently in the stage of deployment of our model. So we are predicting on multiple terabytes of this planet imagery to locate really small surface water features in Alaska. And then we're also developing post-processing and analysis steps in Jupyter Hub and working to kind of distribute these deployment tasks through parallel processing to speed them up, because we are running them on a large quantity of imagery, so it takes a long time. If you're more interested in this project, please check out the poster that is dedicated to it. So that's all I have for my part. I'll pass it off to Mary.
Great, thanks, Andrew. So for the second use case, the above Science Cloud enables simulations of a process-based terrestrial carbon flux model across the Pan-Arctic. So this is work led by Jenny Watts, and it's a collaboration among the Woodwell Climate Research Center, Montana State University, the NTSG group at University of Montana, and other collaborators. And we're using the above Science Cloud to run simulations of the terrestrial carbon flux model, which estimates daily carbon dioxide fluxes and methane emissions across the Arctic boreal zone at 1 kilometer resolution. The terrestrial carbon flux model was developed as a precursor to the NASA SMAP L4C algorithms that are used to reduce uncertainty in global terrestrial carbon budgets. Next slide, please. So the above Science Cloud has been a critical platform for this work. So there's two key steps that I've been using the Science Cloud for. In the first step, we use the Science Cloud to process model inputs. And for this component, we take advantage of the public data repositories that are available on ADAPT, primarily the MERA2 reanalysis dataset. And we also use the high capacity user storage to download additional data sets that we need to run our model. And then we utilize the large number of available compute nodes to process the large input data sets, processing multiple daily files simultaneously, which really helps process these large data sets in a timely manner. And then in the second step, we use the large memory resources available to launch long-running memory-intensive model simulations. And the terrestrial carbon flux model, it updates its soil carbon pools with each daily cycle. So we don't distribute this processing task among multiple nodes. However, we are able to run a long-running task for several days or weeks, depending on how many model cycles are required. But overall, these computing resources are critical for processing the large input data sets and for running the model and estimating daily carbon fluxes at 1 kilometer for the full Arctic boreal zone. Next slide, please. So in summary, these use cases demonstrate the utility of the Science Cloud for image classification and process-based modeling over a range of spatial scales. And with the flexible computing resources, high capacity storage, public data repositories, and the responsive user support, The Above Science Cloud is an important platform for investigating landscape changes and carbon dynamics at regional and larger scales. And one suggestion that we had to help make these tools a little more accessible to current and new users would be to provide some more documentation on just the specific CPU and memory resources that are available on different compute nodes, and some documentation on like the specific locations of some of these data repositories that are already available on ADAPT. And my apologies if this documentation already exists somewhere and I just haven't come across it. But yeah, just in general, we think this would be helpful for users. But overall, these tools enable the above community to enhance collaboration and address these computationally intensive questions around Arctic boreal science.
Thank you. Andrew, Mary, I really appreciate both your talks, and Mary, I guess both of you kind of contributed to these suggestions. I think that they're really good ones, thinking about having more documentation on how to use the data and also documentation on what data repositories are available and where. I wonder, Jordan or Zach, if you guys have any thoughts on that. I see Jim Shoots online too. We can ask him too.
I think it's a great idea. I think there are a lot of README documentations, but something a little more forward facing to almost advertise these would be almost more beneficial.
Yeah, and I feel like when we were starting to talk with you about how to use the PRISM resources,
Yeah,
it was hard to
so good.
find like where those resources were. maybe.
Yeah, once I got them, it was actually pretty straightforward.
Yeah.
But I didn't know they were there.
Yeah, so I think maybe advertising that a little bit better would be good. I don't know, Jim, you're online as well. Jim Shoot is at the NASA Center for Climate Simulation, and I don't know if you had a comment as well.
Can you guys hear me?
Yeah, we can hear you.
Hey, look at that. I'm surprised. I've had nothing but problems trying to get in, so this is great. Yeah, I apologize for, you guys having problems trying to find documentation. I know it's a challenge. We are investigating the use of the implementation of a knowledge base that would be searchable and a little more user-friendly. That's one way that we've done it, or that we've considered doing it. In fact, we just talked about it the other day. So yeah, we have things that we're trying to do to kind of get you the information that you need in a little more timely and easy to find manner. So apologies for that.
If they have a question now, what's the best thing to do? Should they just email support with like questions that they have still, or are there resources we should be putting up on the website now that are available and just not easily findable, searchable?
Yeah, so you have two categories of problems, right? So you have general GPU usage kind of questions and technology kind of questions, and then you have PRISM specific questions, right? Or ADAPT specific questions. So if it's more of the specific question about a resource within ADAPT, then I would say your best bet really, unless you already have a working relationship with some of the folks on the team, like I know there's Jules who does a lot of application support. Bot does some application support. Those folks, they see hundreds of tickets a week, altogether. And so sometimes they might have a good answer for you. Other times they may have to go digging, or in some cases they just may not know themselves, right? So, I think that your best bet is to start with a ticket. And we are trying to get better about our response times on those. I know sometimes you submit a ticket and it kind of goes in a black hole and you wonder what happened. But I've implemented a couple of things to keep the team pushing on tickets so that they don't go stale.
One quick suggestion. So I was looking at the Above website. You could add hyperlinks, like specific resources that your team uses. So maybe like one hyperlink for like the PRISM resources page. One for like how to access the Above Science Cloud systems. That could be kind of a quick win.
Yeah, we could certainly add some links to our page. In the past, we've done that, but I think you guys had a website update at some point, and then all our links are bad. But it's probably time to relook at that and add some new links again. Maybe put that on our site too. Yeah.
Right, and that's one of the things related to the knowledge base is basically a website refresh. I know Laura has been wanting to do kind of like a redesign on it to clean it up, because once they redesigned it, 4 years ago, it started off clean, but then over time there wasn't real clear direction about the hierarchy of the page or of the site. And so you end up with, similar information in 4 or 5 different spots. And so, yeah, we recognize that that's a weakness of the online documentation, and it is on our roadmap to try and resolve that.
Did we have other questions for Andrew and Mary? I had a question for you, Andrew. So you're using some of the planet imagery, I think you said, in your work, and I wondered, I think Jenny has a planet project to do that, doesn't she? And I wondered where you're putting all your planet imagery and kind of, how much of that imagery are you using right now as part of your project?
Yeah, so this is Jenny's project that I'm working on, and so I'm downloading planet imagery through a command line interface and storing it all in the no backup directories on Adapt, or in my no backup directory on Adapt. And currently I have around 2 terabytes, I would say. And I looked at my usage on the Planet website, and that looked like it was about 30% of what they would give me. And I've heard it's not too difficult to request more imagery from them, but they certainly are willing to provide a lot of it for these types of projects.
Yeah, you can probably get more space because you're part of that NASA project. I just wondered because right now I think we don't really have planet imagery for above in a central location, and we had thought about doing that in the past. So I
It's
wonder.
very spotty right now, just because, but
Yeah.
it's slowly building up to expand throughout.
Yeah, so maybe something to think about for the future is, you'd still need to be part of that group to access it because there's the licensing, but I don't know, something to think about. Well,
Yeah, and I'm not sure what happens with access rights after the project is over. What do I have to delete all of that imagery, or could we keep it on Adapt for other people to use later?
Yeah.
I don't know.
Yeah, all right, well, good, that's something to think about, and we thought about it a few years ago, and it's probably time to circle back. So, well, I want to say thank you both very much for presenting, and Mary, you're another one of kind of our power users. I was saying this to Stefano earlier, is that both you and Stefano had over 1,000 jobs submitted in Slurm in the last few months,
Can you
and
tell if they failed or they were successful?
so then there were 100 jobs that were successful, but over 1,000 were submitted. So, but you two had the most. So I really appreciate you putting time into using the system and then giving us feedback on it. Thank you very much.
Yeah, thank you.
Hey,
Right.
hey, Liz, can I just jump in real quick?
Yeah.
There is a space on CSS where I think Mark's group and Zach specifically are downloading that planet data. I think this is a great example of what Andrew just said. This is a great example of finding out what other folks are doing and comparing notes. And maybe there's a way to fold in his data into that structure. I don't know if there's, any changes to the native data structure. But there's no reason that you should have to put 2 terabytes of, something like planet data in your no backup. Because, a couple of reasons. Number one, that's a lot for your quota. You're taking a lot of your quota to do that. But then more importantly, that's data that other people would like. And, that's what we consider a common data set. So we may, one of the takeaways from this week-long meeting may be that when everybody gets back home and everything to talk about how maybe we can look at that data and possibly consolidate it, because there's no reason to have Zach and company download it a second time if it's similar data.
I think we're all under the same NASA agreement. So
Yeah.
putting that onto the sort of the CSS drive of the repository would be exactly quite beneficial.
Thank you. Well, that's why we have this session, to kind of bring everybody together to talk about it. So I appreciate that. All right, next up we have Jordan. So go ahead and take it away.
Yeah, awesome. So I'm Jordan Caravaggio. I work with the System Innovation Lab team, so mostly Mark Carl. I'm actually starting a PhD with Tatiana and the fall of August. It's gonna be fun. So I'm just gonna be talking about some of the work that we have been doing particularly deep learning, but particularly working like with very high resolution data from overview. So the main motivation was we were actually classifying some of these clouds from these images just to like avoid having some of these bad distributions on the data. We were just calculating a lot of indices, we we're getting a lot of contamination. We just needed to get rid of some of that. And we started with some thresholding mechanisms, just trying to get some of those indices to remove those clouds. But then on this very high resolution data, you have like maybe like bright fields that you might get just brightness levels that are compared to the clouds. The other features that were just not good enough for the thresholding method. We then proceed and use a random forest, just trying to use some machine learning base. But since the random forest is actually pixel based, you're only looking at the intensity on a single pixel, we're having the same false positive, like we're having the same issues. So we went ahead and move on then to a kind of deep learning realm of things where instead of looking at that individual pixel or the intensity of that pixel, we're actually looking at the neighboring of that pixel. So we have sliding windows via convolutions where you can actually look at the neighboring of that pixel, extract some of those features, and then learn from that. That was basically the main idea. So you're gonna kind of explain how we're leveraging that, particularly for like our high performance pipelines. The main idea is we train once, and we normally like just have this same model that we then iterate over terabytes of data that we want to classify for worldview imagery. So just ideally, we start with the EVHR process that we have. So we auto-rectify the data, we punch up in the data. We have 12 values that we can then label at the beginning. So for the labeling, we are doing the Windows VMs that provides with a guacamole service. So you can just reach those VMs through the web browser. The nice thing is you have like ArcGIS Pros in there, you have like QGIS. There are several tools that you can use for like annotation if you're familiar with the Windows environment. So once you actually have the training data, then you can actually move on to then more of that pre-processing, more of that like training things that you might need. So for that end, we have several like processes where once we use Jupyter notebooks just for like the exploratory data analysis, like Stefano is doing, just looking at some of the graph of how the data looks like, how the indices might be looking like on specific locations. But then we move on to the like Prism kind of hardcore processing. And the idea is that all of the pre-processing, all of the training, and all of the prediction is done on GPUs. So we avoid having to transfer data between CPUs and GPUs to avoid that latency between like transferring data between the two devices. So we're leveraging some of the tools from NVIDIA, particularly like it's called NVIDIA Rapids. If you want to look at some of the GPU processing, they have a suite of things that are replacing like NumPy, but just moving into the GPUs like QPy. They have several replacements for things that are normally done on the CPU to then kind of speed up your processing. Once we start having our pre-processed data, we move ahead and then train our model. And for that, we use like multi-GPU resources. We can do like multi-node, multi-GPU resources. Kind of depends on the use case. If you have like 1 million tiles that you want to train on, then probably that you can scale to like more systems. And we do have another system within the Prism environment, which is called the DGX, which has like more optimized GPUs, well, the A100s compared to like the P100s that we have, which are like, they have more memory. So you can increase the batch size of your models to then like make things faster. You actually can get 8 GPUs in a single run. So once we have our model trained, we then proceed to do the inference. So we have these large rasters. Normally they range between like 10 gigs and 20 gigs. So you can have rasters that are like 100 gigs. That we might not do them like online and on memory at the same time. So we kind of use sliding windows to then scale things and improve the processing. So I'm just going to present some of the quick results. This is work that is under review right now. We're trying to finally get it published. But the main idea is we train our models on specific locations, particularly like Vietnam and Senegal area. And then we transfer that model just to other locations like Ethiopia and the particular tropics. Now, that was kind of the initial project that we were working on, but then we were asked to do some cloud masking on the actual ball domain, particularly like in Alaska areas, in Siberia area, and so forth. So we didn't want to reuse and we didn't want to like redo all of the training data that we had. So we started looking at how we could transfer those models to other locations that might not look similar. So the idea was that we leverage what is called like transfer learning, but particularly like domain adaptation, where you can have your model that was pre-trained, use those weights or features that were learned on another location, and then retrain it or just move it to another location, and then maybe like modify the pre-processing you do, modify some of those models that you're doing, by then just leveraging few annotated data. So let's just compare that. We had to train on a particular Vietnam location where we needed maybe like 16,000 tiles that we needed to label, we can then just have a couple of like maybe 1,000 tiles for Alaska, like 1,000 tiles for like Siberia, if that was the case, and then just train for a few equals, like lower the training time, lower the amount of training data you need, but it's just expensive, and then just have some of those results. We're currently working on publishing this work as well, which is more focused on how you can have more than regional models, which it's oftentimes harder with deep learning models since they are kind of distance based. So if you have a let's say intensity of pixels that it's really different between locations, the models are so oftentimes lazy. Like they kind of go with the easiest path instead of trying to learn the features that you might need. So it's just some of the actual validation results that we have so far. Particularly looking at some of these locations, we're getting an average of like 94% of accuracy over the actual areas. We're getting that validation by like manually looking at some of these imagery and then labeling actual real points from some of these data to get kind of like an accurate product. We are generating like cloud optimized geotips. So the main idea is that at some point, once we generate all of these set of terabytes of data we're processing, that you can just look at it via like a SMC, which is the science managed file environment that we talked about. Then like look at the actual layers that we have, but then having those cloud masks on the lower end. So you can just mask those clouds out and then do better processing of things. So just as a summary, touch base on some of the resources that we kind of used. Touch base on how we can actually leverage deep learning, but in more than regional locations, just not focusing on a single location, but kind of expanding more like heterogeneous areas. And then last thing, how we can actually leverage GPUs to accelerate most of our pre-processing and most of the processing that we need. Any questions? Thank you very much.
I have a question. So when you are doing this in Alaska, do you have issues with like snow on the ground, or Siberia too, like snow looking like clouds? Or
Yeah, so this is how it kind of started. Like the same model that we work on Vietnam and Senegal, we were able to just transfer it and generalize over Ethiopia. That was pretty easy, basic. Once we moved to the Alaska domain, we actually noticed that we were having issues with like snow. We were actually having issues like there were some locations of like water that was just appearing like that's really bright when we looked at it. So we started labeling just a few training files just to get some of that, let's say, diversity of Alaska and diversity of Siberia to then get better models. So yeah, it wasn't problematic.
but you can separate out like snow from clouds?
Yes.
Oh, that's
Yeah.
cool. Right.
Yeah, right now we're just using RGB and infrared bands,
Okay.
and the CNN is actually able to get some of those features out of those bands. Like future work, we're actually planning on transferring the same model to then like other sensors, like planet labs and so forth. So it's gonna be some exciting stuff to come.
Thank you. And I see your paper's under review, so can't wait to see it when it comes out.
Hope so.
He couldn't show us all the results because they're under review right now.
Yeah.
So we appreciate that you could show us what you could. So
Appreciate it.
thank you very much. I think we just have one left. We're doing pretty good here. Yeah. Okay. Last but not least, we have Debjani from the Oak Ridge National Lab staff. Tell us about that and issues with the bug.
Yeah. Okay, thanks, Liz, and good afternoon, everyone. I'm Debjani Singh from Oak Ridge National Labs Distributed Active Archive Center. And I'm going to talk about a snapshot of what we have for the above project at our DAC. Okay, so as you all are aware of, the Oak Ridge National Labs Distributed Active Archive Center, or the ORNL DAC as we call it, is the primary data archive for NASA's terrestrial ecology and carbon cycle programs that specializes in curating, archiving, and distributing the data on terrestrial ecology. And above is one of the projects or one of the active projects that we have in our DAC that we are working on. And as you can see, oh, sorry, it's a little down. So above is now the largest ORNL DAC projects in terms of volume of data. So it's going pretty good. And
I think Bruce in his talk, he's gonna.
Yeah.
show a-
Yeah, I,
show that.
yeah, and I have some more details, but Bruce is going to add more to it, yes. Okay, so most of you here are aware of our ingest process. It involves data submission, data curation, and data publication with a little bit more details on how do we do it. We interact with the data provider in the beginning to get all the data files. We check those data files to figure out if the data looks reasonable. We have also identified algorithm problems during our QA. So it's a good thing that we check your data. And then we iterate with you all to get the data corrected or, like in the right format that can be used by users in the future. And then we document your data so that the users can understand it better, and with your help, of course. And then we stage the data in an archival format and we share it with you all to review your data before we publish it. So that's the detailed publication process that we have. So many of you interact with me while you are, like archiving your data, that what is the status of my data set? So this is how our publication process works. So your data is in these various steps, depending upon, like when you have submitted the data. So as of today, we have 8 data sets pending submission. So Liz and I, we work very closely on getting your data to us, either through the above data cloud, above Science Cloud, or through personal contacts, like bugging data providers. Either Liz does it or I do it. Get us your data. Okay. And there are 5 data sets pending QA. So we are working on those 5 data sets. There's 1 which is pending documentation, and there are 5 in PI review. That is, we are waiting on the data provider to review their data set one final time before we release it to the public. Now that was the usual DAC publication process. However, like there are scenarios when you don't want to follow the usual DAC publication process, right? Because it might take more longer, means, like depending upon how many active projects we are working on, what is the requirement, or what are the priorities for those projects. So we have something called as preprint data sets, which is because nowadays journals require that original data is archived when you submit your manuscript. So we have a workflow that provides for a preprint data set in which we provide you all a landing page with the original data files. Now those data files are not QA'd, like it is just in the same format like you have submitted to us. And then we provide skinny documentation with the data files, just with basic metadata for the reviewers to understand. Then we provide you with a resolvable DOI and a citation that you can share with your reviewers so that they can access your data files. However, one request that I would have for all of you is, when you want your data archived before you submit your manuscript or at the time of manuscript submission, please list it in your request for submission so that we know that, okay, you need it right away. Because, in that way, we can prioritize at least this resolvable DOI to you while you are submitting the manuscript. And how will your reviewers know, that this data set is a preprint is by that yellow banner that you can see. And also, if you click on that link on the yellow banner, it just displays our policy on preprint data sets. Okay, so another scenario is when you are updating your data set. Like there are a couple of scenarios in here that you have a data set that you provided to us and was published, let's say in 2019, with the data from 2010 to 2019. Now you have continued working on the project with further funding, and you have your new data set from 2019 or 2020 that you want to be added to the existing one, right? So in cases where you don't have any changes to the already published data files, then we just add the new data files, either spatially, like increased area, or temporarily. Okay, yeah. Or temporarily, like longer time. And we provide you with this, the DOI and the citation remains the same. Only the version changes from V1 to V1.1. However, if there are corrections to the existing published data file, if there are any algorithmic changes, then we provide you with a new DOI. The old DOI is superseded with the new one, and the version number changes from 1 to 2. As you can see, we have 9 above data sets that has been appended with new data files, and there have been 4 which we have new versions on. I'll run through this quickly. Like it's out there on my poster also. We have published 150 above data sets across the various sub-projects and above. And here's the metrics over the years. So 158 total data sets, 280,000 file counts across all those. And we have almost 26.3 or 26 terabytes of data across the project. And again, my bad, it has gone down.
I think it's just how it shows on the screen. Yeah.
Okay, so since January 2015, the data has been downloaded multiple times, I think, can you see that, Liz? Yeah.
It doesn't show how much.
Oh, okay, yeah, it's just, yeah, my formatting was bad, yeah. And it has been cited 80 times, and there has been 10,000 unique users, who has downloaded their data. Okay, and couple of tools at ORNL DAG, the spatial data access tool, which helps you format your data and download it in any ways you want. We have the Earth Data Cloud, which is analysis ready, and you can do your analysis in the cloud. And we also have the linkage that Liz talked about with the Above Science Cloud, where you can upload your data, we get the metadata, archive it, and we again send it back to the Above Science Cloud for you to access it. So it's bi-directional linkage. Because you are one of our biggest stakeholders, so if you have pain points during your data submission or during the ingest process, please feel free to reach out to me or any of those emails and let us know what your pain points have been. We are looking to improve our process every time. So what improvements do you want, to make your data more user-friendly or, to help you get it to the users easily? So feel free to reach out to me. My email is debd@ornl.gov. It's not in here, but if you email to ingestlead@ornl.gov, I get it too. So, okay, that's about it. Questions?
I looked back at your presentation online. So it's been down, the data for above has been downloaded 43,000 times from 10,000 unique IP addresses with at least 80 data sets and
43,000 times, yeah. So, yeah.
I'm just curious what who uploaded the huge data set in 2018?
Paul Montesano. 164. Oh no, 2018 was about.
Was a big year.
Oh yeah, 2018 was the average NG.
Oh,
Okay, I thought the number of files was this year has been the largest. Is Paul Montesano's 164,000 files that we got. Yeah, the Elvis one. Yeah. But we have a CMS one, which has 650,000 files. So that's the biggest one that we have in the DAG. And then it's Paul's, So yeah.
This may be a slightly ignorant question, but so you mentioned how you have the metadata clusters for all these data sets. Is there sort of almost like a SQL search GUI for querying the metadata within these data sets? Because as you're expanding over an entire, the entire above and beyond domain and all these different data sets, is there any tool available for specifically quickly highlighting certain testbed areas?
So you can do it through the Earth data search, yeah. So because we submit our metadata to the common metadata repository, the CMR, and then it's pushed to the Earth data search, and you can do that. Yes. Yeah. Did that answer your question?
Yes. Perfect.
Well, I just want to thank all of you for coming today and for everyone online. It's really great to get this kind of feedback and have this discussion. And I know we're a smaller session, but I think it's given us an opportunity to really talk about some of the really issues. And I appreciate you taking the time out of coming to us. So thank you all so much.
Yeah.
One point of clarification. Andrew and I talked about the CubeSat with the Planet Labs data. I just want to give a quick shout out to Allison, who wasn't mentioned that much, but she got everyone really set up working with that early on. So she was critical to have help with that as well.
Yeah.
I'm going to be shooting you guys an email about Lancet.
Yes,
I gotta run now. Outside, but I'm
we're
going
hoping to have it
Yeah.
up by this meeting, but now it's.
Yeah,
now
that's
it's
no
June.
problem. Yeah,
That's how it goes.
yeah, no problem.
But no, we're originally, so I think what we're trying to say is we're originally going for just the above domain, just to make sure we have our.
I mean, that's where I'm working, that's where I'm getting the model
Well,
running.
initially just the above domain, but the end goal is to have a global data set. for it, so we can. Yeah, talking about, what do you say, Siberia?
What about Central too?
I'm not sure about that, I would have to ask, but I know like. the
Like you
landscape-
have a request, you kind of say, hey, this is gonna be useful.
And this is what I'm shooting for.
Yeah, that can be.
Okay, yeah, I'm gonna shoot you guys an email with a little more details, like how I do it, what I'd be looking for, yeah.
Yeah, please do.
Yeah, that'd be awesome, if I can, that's the only step I use Earth Engine for. Yeah, I can go directly to one computer, I'm all for it.
Right, right. Yeah, so, and then, especially where we're looking for other areas, because we want to segment the globe up, so the Siberian boreal region would have an immediate use.
Yeah, of course, yeah,
So
yeah. I'm not the only one like up on an island.
Being that we can adjust the timeline for that.
Yeah, cool.
I don't know what like the next thing will look like. Yeah. Something different, because now so many universities have, for instance, computer labs, they didn't have one.
We done? Yeah, we're done.
Yeah, like a lot of changes happen in how options are so different, so, you know, for the next. There's nothing.